Hello and welcome to Easy Projects. So today we'll take a look at switch mode power supplies or switch mode regulators, and we will be looking at the step down configuration. So what is a switch mode regulator? Well, to explain that, I think we should first take a look at a linear regulator like this LM317. So I will try to explain how this works first. So if we take a standard NPN transistor like this one, we would easily be able to choose a resistor here that could drop the voltage down from 10 volts to 5 volts here at a given load. But the problem comes when this load changes, because then this voltage will change. So inside a linear regulator there's some circuitry that will apply more or less current to the base of this transistor depending on which way this voltage needs to be corrected. And actually all we need to do that is one single op amp. So connected to the non-inverting input of this op amp is a voltage reference. We could say this is 1.25 volts. And to the inverting input we have connected the output through a resistor and also a resistor to ground. So when this voltage here is 5 volts, we want to set these resistors so that it matches exactly 1.25 volts when it is divided down. So say we turn this circuit on. This op amp will of course be powered as well. And we can just imagine this is a perfect op amp for the moment. So we turn the circuit on and we apply power to the op amp. Well, this node will immediately be at 1.25 volts. But this will be at 0. So the non-inverting input is higher than the inverting, so it will turn on the output. So current flows into this pass transistor. And when this node gets just above 5 volts, the op amp will turn the output low. But as soon as this drops below 5 volts, it will turn the output on. But it actually doesn't do that, it just finds a steady state and it will maybe be half on or something like that. So if a high is 10 volts and a low is 0 volts, it might be sitting at 5 volts. So now we go and change this resistor. Say we put another one in parallel. And we just doubled the load. So this voltage will drop. But this loop responds very fast. So we will not even notice a drop here. Or if we connect up the oscilloscope, we might just see a tiny little spike going downwards. So the op amp corrects this voltage, and now there might be 6 or 7 volts at the output. And these voltages are not correct, this is just something I wrote down. I have no idea about the actual voltage inside an LM317, but it will likely be much lower. So this does a pretty good job at regulating this node down to 5 volts. And let's say we are pulling 1 amp through here. That will of course mean that we have to pull 1 amp over here as well. But we have 10 volts here and 5 volts here. That means we have lost some energy, and all that energy is dissipated in this pass transistor as heat, so this will get very warm. And we'll just waste 50% of the energy as heat. So wouldn't it be smarter if this transistor was not allowed to be either half on, half off? It could just be basically off or on. But that would of course mean that this voltage will go between 0 and 10 volts. And we can't have that. So we'll need to put something in between here that can store the energy while this is off. And that needs to be charged up again once this turns on, so it will not immediately go to 0 and it will not immediately go to 10 volts. Well, that is exactly what a switch mode regulator does. So let's move on to that one. And I have just taken the datasheet from a typical switch mode regulator, the LM2576. And we're looking at the block diagram. And in here we will see some familiar components. We have the transistor here, we have the voltage reference, and we also have the op amp. they call it a error amp here. And if it is adjustable, these two resistors will just be outside of the case. So what we also have in here is an oscillator, a comparator, a NAND gate, and some driver circuitry. And there is all sorts of protections and resets and stuff like that, but who cares? All we want to know is how it works. So we can just ignore all this. So I have drawn another schematic where all this reset and control circuitry is not there. So let's take a look at that one. So I have just replaced all this with some components that we already know. For the oscillator, I chose the CMOS 4069 inverter chip, as I've used a lot of times now. So I'm generating a square wave, and I'm feeding it into an AND gate, so this is not a NAND gate. I'm also taking the output voltage and feeding it into an op-amp. I have a reference, but I have swapped the inputs here compared to the schematic in the datasheet, because I'm using an AND gate and I want to AND these two to get a high. So this AND gate can only be high if the oscillator is high and the signal is high. So if this is too low and it needs to be pulled up, then this will go high and it will stay high all the time, but it will only switch on this transistor once this signal goes high. So it is forced to turn off at some point. So when this transistor turns on, it will try to push current into this inductor. And let's say we're trying to draw 1 amp of current on the output. Well, this current through here cannot rise to 1 amp instantaneously. It will need to ramp up because of the inductor. Because inductors will try to resist changes in current. Well, that is just fine. So it will charge up this capacitor until it gets to 5 volts. This will go low, and this oscillating signal cannot turn the AND gate on by itself, so this will also go low. So the transistor will just turn off. Well, we still have this inductor here, and it will still try to resist changes in current flow. So that inductor will still try to push current down this way. But this transistor is turned off, so that is an open circuit. And this one here is connected to ground through the load, of course. And this will of course stay at 5 volts because we have this capacitor here and we have it connected to ground on the other end. So the only way that this inductor can force current into here is to take it from the ground. I know that sounds a bit confusing, but that is actually what's happening. So before we would have 5 volts here and 5 volts here. We can just pretend there's 0 ohms across the inductor. Well, that is not the case, but let's just assume that it is like that. Well, then if we cut the circuit here, that will mean that this voltage has to drop to below 0 in order to allow current to flow through this diode. So it will actually drop to like minus 0.6 volts or something. But all this of course happens very quickly. So once the inductor has got the current that it needs, this voltage will start to drop. And once it drops below the 5 volts, the op-amp will turn on again, and it all repeats. And that is the very basics of how we could make a switch mode regulator. But let's just try to take a look at this inductor in a bit more detail. So what actually happens to this inductor is when you draw current through it, let's say we put it in here and take it out here, the inductor will create a magnetic field. Just like an electromagnet or a speaker or anything like that. But in this case we don't want it to move anything, we just want it to be there. So that when we suddenly remove the current and we cut this wire, then this magnetic field cannot sustain because there's no current through the inductor. So the magnetic field will collapse. But once this magnetic field collapses, it will create a voltage in the wires. And when this wire is not connected, the voltage will be very, very high. and the voltage across the inductor will have the positive on the side that you try to draw current in. So we try to draw current this way, so we'll get the positive here and we'll get the negative here. But if this is at ground, that will mean this have to go negative. Or if this was held at ground, this would have to go positive. But this voltage only gets real bad if you either cut the wire, open a switch, turn off a transistor or something like that that is connected to either here or here. So what we do in the switch mode supply is to connect a diode here and down to ground. So when this goes negative, the current can flow up through this diode. But when this gets positive, nothing will go down here. And I should also say that it takes energy to create this magnetic field, of course. And that is why we see the ramp up as well. Like that, when we apply current to an inductor. This is also the reason why we cannot pass high frequency signals through an inductor. Because all these high spikes will just be used to create and collapse a magnetic field. So we'll get something like this when it gets through the inductor. So I'm not sure if that was a good explanation, but I hope you get it anyway. So I'll try to see if we can actually see that negative spike on the oscilloscope. So I have set up a very basic circuit here. I have 6 volts coming in on this side over here. It goes through these 2 inductors. I just put them in series to increase the inductance a little bit. And it then has to go through these 3 100 ohm resistors, and they're in parallel. So that's about 166 milliamps. So we'll try to take a single shot at the scope when I remove this pin very fast. And that should make the magnetic fields of the inductors collapse. And since this node is held at ground, this one have to drop negative. And I think we will be able to see that. And here we go. And we can very clearly see it on the scope here where, well, there should only have been one, but I must have made contact one extra time with the wire here. So let's try that again. Oops, didn't get anything. And there we have it. And the scope is actually set to 100 volts per division, so we're getting 1, 2, 3.5 divisions, so that is 350 volts just by removing the wire at 150 milliamps. Well, I am not sure that this is correct. I don't know if the scope probe or something could have influence on that, but it is a lot, and it can actually destroy transistors and something if you forget to add the diode. And if you saw my video about the Christmas tree hack, I actually forgot to put the diodes on the transistors on the output of the H-bridge, so oops. But again, this voltage will only come if you remove the pin just like that. It will not come if you slowly ramp down the voltage, or by slowly I mean a few divisions here. So as long as the current has time to get away when the magnetic field collapses, then there will be no voltage spikes. But if you just suddenly remove it, then you will have these huge spikes. So now I have added the diode in here, so we shouldn't expect that negative peak to come now. And I'm using a Schottky diode. That is usually recommended by the data sheets to use that. So let's try to remove this wire again. Oops. And we had nothing. Nothing. There's still nothing. Nope. now we don't get anything, so that diode seems to solve that problem. So I think it could actually be fun to build up this basic circuit and see if we can get it to work. I think we should be able to, but I don't think the output will be that clean on this one, because I have no idea about the best frequency, if the duty cycle should be 50%, this resistance, if there should be any, and what type of transistor we should use, and not even the correct value inductor. So I'll just take a guess and I'll try to build something up and we can try to test it and see if we can get it to work. And by the way, I added this diode in here because I'm using a negative 3.3 volt rail for the op amp, so that this won't drop to minus 3.3. So I have built up this exact circuit on the breadboard, except that I'm not using a reference. I just use the input from the power supply and I divide that down. And I have added some decoupling caps everywhere because this generates a lot of noise. So I have set the reference to 3.5 volts and I will try to probe the output, so we should get that. And we do. And it is actually very clean, but I don't have any load on there, so that could be why. So if I put this 1K resistor in here as a load, it hopefully should still regulate. And it does. But now we're starting to get a little bit of ripple there. I am only using a 100 microfarad capacitor on the output though, so we could maybe improve it by changing that. But this is also in a breadboard and there's resistance everywhere, so... And all these wires will also act like inductors and make switching noise, so what will happen if we connect a 33 ohm load instead? Oh, the output voltage have dropped a bit and the ripple got worse, so I wonder why it dropped. Let's try to measure the base of the transistor here. Well, that is basically just the oscillating signal, so that could be why. So the transistor is on for as much time as we allowed it for, so that's possibly why. So let's take a look at the feedback voltage. That should be the same as the output. So this is what it is seeing. And the reference voltage, that is nice and clean, so that is not a problem. So I think it's either the inductor that's too small or the capacitor. So let's try to change the capacitor first. And now we're getting 3.3 volts as the max. So I've changed the capacitor to 1000 microfarads, and let's see what happens if we connect the 33 ohm load now. Well, the ripple got better, but whoops. But the voltage is still dropping, so there must be something else wrong. So let me try to double the value of the inductor from 100 microhenry to 220. Well, so that actually didn't help. Now it is at 2.8 volts. So it might actually be the current through the transistor instead that is limited. Maybe the AND gate cannot provide that much current. I actually don't know the peak current through here when we are working with a switch mode regulator, so I can just try to change this transistor to a higher gain one, and let's see what happens. So I put a Darlington transistor in there, and that just made things even worse, so now we're down to 2.5 volts. But there is also a larger voltage drop on that. So I've only got one idea left. It got worse when we put a larger inductor in there, so it could be that our switching frequency is too fast for the inductor, so we cannot charge up the inductor before the transistor switches off and it goes back to 0 volts again. And that would of course mean that we cannot get enough current through it. So I can try to change this capacitor in the oscillator circuit to a larger one that will slow down the frequency. So I'll just give it like 10 times more capacitance. Oh, so that did actually help. Now we're up to 3.44 or 3.5 volts again. But now we will of course get more ripple because the frequency is slower, so we are not charging this as often. So I should probably just have put a smaller inductor in there, but I don't actually have less than 100 microhenry, so I cannot do that. So I just put the 100 microhenry inductor back in, and as you can see it have improved a little bit, so I think that was what was going wrong. So, but if I just drop the load by 1/3 here, it is actually not that bad. So we can also try to see how fast this is to regulate. So I have set it to single shot capture when I switch the load on, and I'll just connect the alligator clip over here. Sorry you can't see that, but I'll do it now. Oh, we didn't get right on the edge there. And there it is. So this is at 1 millisecond per division, and that is just fine. You can see we start to get the ripple once I connect the load, but there is actually no transient here, so I'll just try to zoom in a bit to say like 100 microseconds per division. And I think right here is where I switched it in. You can see the signal is clear over here, but we start to get the oscillation going here. And there is still no transient, so that is actually a little surprising, I think. But again, it is only 70 milliamps, but I thought that would be enough to do something at least. So here is just an example of the signal at the base when it is actually regulating. So we can try to pause this. And we can see that it is indeed switching on and off. And this will be one period of the oscillator from there to there. So if we probe the oscillator, that is this one here. And the output of the op amp is this one here. And where this is high, this is where the oscillator is off, so it is actually still trying here, but it can't because the oscillator is low. So when these two gets combined, we will get this signal, and that is the same as the base of the transistor. And here is the emitter of the transistor. So that would be the input to the inductor. And here we are measuring the output. So that would be the other side of the inductor. And you can see just across the inductor there is a huge difference. So I've just added the part numbers and the component values on the schematic here. So if anybody wants to use it, it's here. So I hope you liked this quick talk about the switch mode power supply. And I am planning to make a DIY power supply using a switch mode regulator IC. So I do expect that to work, probably. Well, instead of all that playing around I did with the breadboard, you can of course just make the calculations and choose your component values from that. But I don't really know the formulas, so I would have to look those up, and I couldn't be bothered, so I just tried it out. But anyway, this actually worked a lot better than I thought, and it seemed to regulate pretty good when you got the values correct, so I will definitely try to play around with that a little bit more. But anyway, if you liked the video, please give it a thumbs up and subscribe to my channel. See ya! And thanks for watching.